it is not wrong to be. I would like to say, I mean, mathematically, what you have done, yes, the resultant value is zero. I mean, the resultant electric field, what you found is zero mathematically, but we knew that it cannot be zero, right? I mean, the electric field here at this point, at any point or at any point in space, due to the charge sphere, due to this charge sphere, any point in space shouldn't be zero. And even though mathematically what you did is correct, but we have to revise. I think we have to do some analysis. And I think I know what is the reason. Because of this, because of the ambiguity, the ambiguity that causes the lower limit when you substitute into the variable r, the capital R here. So the entire result will be that causes the entire result to be zero. So in other words, what I'm trying to say is, just give me 1 minute. So what I'm trying to say is, I don't know why it's not right. Wait, just give me a second. Sorry, guys, just give me a second. My tablet is not working suddenly.
For FOAT today, we have this software 202 from Visual Distributed Exhaust Systems EMF or MATLAB software. So these are the two boxes involved for this lab. And the total cost is $127,950. The existing software that is the book, and we support around 157 students for these papers. Yes. Yes, that's right. For these papers, this section.
Okay. All right. So sorry. Okay. So what I'm trying to say is, there is some ambiguity. So in fact, for this expression, for the lower limit, I also can write as, is correct, right? It is correct, because if you see carefully, I can factor out the negative, right? And it becomes h minus r squared. So these two are the same. Yes, these two are the same. So this is the ambiguity that I'm talking about. This ambiguous. So this is the ambiguity term that causes why your answer is zero. So I mean, so R is equals to H minus R. So now if we if we rewrite this,
the old robotic arm can only support writing by people using robotic arm pattern and doesn't cover the additional features
okay.
that this kit
So now this is going to be
kit with full feature as listed here.
it will be this, I think, H plus R
And particularly
plus
for these tables.
uh, R minus H, right? Minus.
It's in use for around
Sorry, just let me rearrange a bit. I just need to get a bit more space here.
yes, yeah, I did inquiries to the department of the proposed to purchase why the new robotic arm, I mean the existing robotic arm that is why are we proposing this? So they mentioned that it's needed because they need the additional feature to for more broader experience.
So this is where I mean this part here. This is where I substitute H plus R into capital. I mean the upper limit to the capital R. This is what I have, and H minus R
Yes, sir.
H minus R plus minus, right, negative H plus R, then
I will need to check. It's probably inside the
minus
code, not I get it for you
H
to
plus R. Yep. Okay. So we still have one dr here. Okay.
yes, it's enough because
So this is where I substitute the lower limits into capital R. So these are the terms that I obtained. So I think should be right. Okay. So if we work out here, so H and H is cancel off, and first this first square bracket result as 2R, and here as well, H minus H, negative R minus R, we get negative 2R, right?
I would say it's
So 2R minus 2R minus 2R,
sorry,
so negative negative is positive.
this particular equipment is also used in the industry at the intermediate level.
So therefore, E of Z
And not used in the industry. No, this is the lowest group.
So we have 4R dr. Okay. So I should have dr term here.
Our minimum is 3, so we got 3 rotations. Which is for working shop 6 line supplies, the total of 14,500 with the lowest goods. So this is a pencil machine with a total price of 1,500. Students diploma mechanical, mechatronic, bachelor level mechanical, bachelor level mechatronics, and support the following courses. These are machine. That's all from the EQ.
Okay. So it's r squared. Sorry, because here here there's a r outside the bracket altogether. I mean, I should put another bracket here. Yep. So the first square bracket, as I said, is 2r minus 2r become 4r. 4r multiply r, then I get 4r squared. And here, here we get integrating r squared. So we will have r cubed over 3. Zero, sorry, is from 0 to a. Sorry. Okay. And we can rewrite this term as 4 pi epsilon naught h square multiply with 4 pi over 3 r cube, a cube, right? So there's a the inclusion of pi you will see later on why I do this. So since, oops, sorry, since rho v is charge density, so we can is equals to charge density. So the charge density of the sphere of radius a. Okay. Therefore rho v can be written as the total charge distributed over the volume, right? Distributed over the volume. Okay. So this Q here is the total charge. The total charge contained in the volume. Okay. So by seeing this, so we can say now, so Q is actually equals to rho V 4 over 3 by a cubed. So that will be the total charge. So rho v multiplied this term is my total charge. And I can write, therefore, the electric field at point at point P, so it can be written as Q to 4 pi epsilon naught h square. So if we want to add a direction, so the direction here is in a z direction. So in general, because for a sphere, for anywhere in space, because we take one point in I mean a point in space which is along the z-axis. So by right, in general, the electric field from a sphere, from a charged sphere, so in general, the electric field from a charged sphere E should be in somehow is 4 pi epsilon naught r squared r cap. So it's not too much away from a point charge, right? It's not too much away. I mean, the expression that we have is not too far away. It's not too far away from what we have for a point charge. So we will encounter this expression. I mean, this type of expression again, especially those we have discussed for infinite line charge, infinite surface charge, and spherical charge, spherical volume charge. They have the same expression when we apply Gauss's law. So,
Sorry, can I just check whether I still needed it?
so I,
Okay,
I, I, so for the working that you have done, as I said, mathematically is not wrong when you do it. The working step is correct. But however, I mean, physically, we should know that there's some kind of electric field at this point. It shouldn't be zero, as we have discussed. So I mean, at some point we have to pause for a while and think, is this right? Even though mathematically it's correct, but logically is this right? So you have to somehow we have to check. Maths is just maths. So I think this is one good example to show you that um, most of the time, um, the mathematics will give us uh, a satisfactory answer. However, we have to look at it. If let's say things that I mean things that didn't really look logical, and why? So it seems correct. So we have to analyze in some way that why should I what happened? It shouldn't be zero. I mean, you should ask yourself. So this exercise, I hope it serve a good exercise to you, serve a good example to you, and we shouldn't sometimes too much rely on the final answer from the maths. So you have to justify, even if you, let's say you get zero, you have to justify why is zero. I mean, yes, the maths is correct, but it shouldn't be zero, right? It shouldn't be zero. So that's the line of questionings that sometimes you are required to perform. Okay. So, so I think that's the end for chapter one. That's the end for chapter one. And um, after this discussion, after what I've shown you, uh, in the tutorial, I think you can almost attempt all of the questions. You can almost attempt all of the questions. So I've discussed until question 3 last week or this week, I think. So I think you can try the rest of the question, 4, 5, 6, 7, and 8. And in particular, 7 and 8 are similar. Yeah. So those examples that I have demonstrated to you in the lecture, you can apply the methods that I have taught you. So 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 you should attempt this. Yeah, you should attempt these questions. So to test your understanding. Okay, so before we move on uh, to the next part of the to the next chapter, any things that you would like to clarify? No, no. Um, from from my point of view, and I think Gauss law, they have their limits. Yeah, it's not because of Gauss law. Um, as I said, try to explain to you, because there's an ambiguity in there's an ambiguity for the lower limits. So which I've just explained here. Yes, you can apply Gauss law for a uniform charge sphere. Yes, you can apply Gauss law. So I will show you later. There are certain criteria or certain condition where we cannot apply Gauss law. So Gauss law is a special case. I would say is a mathematical tool for us to analyze simple structures, or some approximation to a complex structure using this mathematical tool. Okay, so this complex structure, we will that we have to do some assumption. Of course, we have to do some assumption, and that will enable us to apply this Gauss law. Gauss law is not applicable to all situation. So as I'm trying to emphasize since the beginning, um, which I always say, there should, I mean, when we talk about reduction of the difficulty in the integration, so we should always look for the symmetry the symmetry point of view of the charge distribution. So when we try to apply Gauss law, we will also look at the symmetry distribution of the charge. And if the symmetry property is not fulfilled, is not satisfied, if the symmetry property is not satisfied, then we can't apply Gauss law. And that's the I mean that's the limitation of Gauss law. So we'll look into that in the coming chapter shortly. I mean, maybe not in this half an hour time. Maybe I don't think we can cover in half an hour time. So besides that, anyone would like to clarify certain things? Is my explanation to you so far you are able to follow? I mean, from the starting of today's lecture, I mean, the explanation that I provided to you, it makes sense to you? Okay. So we'll move on to the next chapter. So please remember, um, try to attempt all tutorial questions. Try to attempt all tutorial questions. If you have problems, please come to me, discuss with me. Oops, sorry. Uh, okay. So here we will learn Gauss law, chapter 2. So before we um, look into the concept of Gauss law, uh, first we will learn some new definition. We will learn some new definition. So one of it is called the electric flux density. So the electric flux density is a new definition of vector which is defined as d, the electric flux density, equals to the permittivity of free space. So this is called the permittivity of free space, multiply with the electric field. Okay, so this is um, in free space, and this always holds true. But by right, so free space mean you can consider in air. Free space means the medium. So we call this the medium in free space is air, for example, air and vacuum. Excuse me. So So this holds, I mean, this relation holds, and in general term, it could be written in a more in a more general form, which is in general, it can be it can be written in general. D is can be written as epsilon not epsilon r multiply E. So which is D equals to epsilon multiply E. So this represent the epsilon r is the relative permittivity of the medium. So this relative meter, uh, this is the medium where the electric field exists. I mean, so we can actually calculate what is the flux density in the medium. So the electric flux density in the medium. So it is always written as epsilon naught, which is the permittivity of free space multiplied with the relative permittivity. So here we call epsilon r. It is called the relative permittivity of the of a medium. So this epsilon naught is always fixed. However, for different medium we have different relative permittivity. Okay. All right. So the dimension of electric flux density is Coulomb per meter square. So that's the dimension. So if we have an electric field here, so if we have an electric field um, passing through a surface, so we call that the flux lines. So this electric field that passes through a defined surface. So let's say we define an imaginary surface. Okay, we define an imaginary surface. So now we will talk about this imaginary surface as open surface. So this surface here, the surface which is shown to you here, it is called the open surface. So why is it open? Because if you want to compare to a plastic bag, so if you take a plastic bag and then you tie and then you close both ends, normally a plastic bag is open, I would say. At open is one end, right? So the plastic bag is open at one end. So if you tie if you close it the end, so there's no um, open area that you can access into the plastic bag. So it is called a closed surface. It is called a closed surface. So here it is an open surface. Okay, it's an open surface. So this is by definition. Yeah. So if you, as I said, if you understand the closed surface as a plastic bag, and then here you should know that this is an open surface. So when D is normal to the surface, then the flux is maximum. While if if the electric field lines is is parallel to the surface, then is zero. That means if D is tangential to the surface, if that means that So for this case here, if it is perpendicular like this, so that will be 0. So the evaluation of the dot product is always maximum when it is normal, because this area here, um, I always mention, um, in chapter 1, we will use the surface area. We should associate the surface area, which is the direction of the surface area must be perpendicular to the surface, right? So when I mean, here we can see the reason. We already see what is the reason as we approach this problem. I mean, the evaluation of the dot product, the electric flux density when we dot it with the surface. So if the direction is, it is not in the same direction, it is not the same in the same direction of the it is not in the same direction with the normal to the surface, then it will be then it will be what? If let's say I put another point here, so in general, if D is some angle, is at some angle, it's at some angle to the surface. So D can be written as cos theta at some angle theta. So let's say I put I put a red line and I put a red line and blue line just to distinguish them. So if it's some angle, okay, if let's say this is for your, so if D is at some angle here like this with respect to the normal to the surface at some angle theta, then our projection, the projection of D, so we want to find what is the effective flux through the surface. So what is the effective electric flux density through the surface? So we have to apply the dot product. So if it is some angle, so we want to find the projection of D. Let's say this is a projection of D onto the direction that is perpendicular to the surface. So that is, we sometimes we call the effective electric flux density through the surface. So this is what this is how we define it. So therefore, in general, if D is some angle, then the evaluation will be the dot product with respect to the normal direction of the surface. Okay. So here we can see if theta is 0. So theta is 0, that means the D direction, the flux density direction, which is the same as the normal direction of the surface, then it is maximum. And when D is tangential, that means if the flux direction, if the electric flux density direction is perpendicular, it is perpendicular with the direction of normal to the surface, then it is zero. Okay. So flux lines, here we so when we present electric field, so electric field that we studied here is always static, is not dynamic, so it is never change. And if we see carefully, if we're going to evaluate D, if we're going to evaluate D over some surface, right? So if we define just now from the earlier slides, we call flux, right? D phi, D psi. So so this psi is D times some surface, right? Some small area. Oops. Some small area. Okay. So which is our definition here. Which is our definition here. And therefore, integral of um, therefore the C C is actually the integral of d C integral of this term here. Okay, so if we look again at the definition of electric flux, so if you look again the definition of electric flux, so this term here, the dimension is coulomb per meter square, and this term here is meter square, right? Is the area, right? So that means the flux that we are going to have, I mean, this dimension here is coulomb, which is the charge, basically, right? Which is the charge. So later on, you see that in Coulomb's law, we will use this term again, which is based on electric flux density, and therefore flux actually represent the charge. So therefore electric flux actually from a charge Q has the same value as the charge. So this is what it means. So electric field intensity is dependent on the medium where the charge plays. So in fact, as I said, the electric field should be written in a more general way, where Q is 4 pi epsilon naught epsilon r squared r cap. So in the direction of the in the radial direction, coming out from a point charge. So here I can written it as epsilon as a single term. So the vector field is also is independent of medium. Is independent of medium. So since D is equals to E multiply the permittivity, right? So therefore we call D is independent of the medium. So it's not dependent. However, the electric field is dependent on the medium. So sometimes flux density is called lines per square. The lines as the electric field lines per square meter, and is measured in coulombs per meter square. So Coulomb's law, basically we define electric field from Coulomb's law, and subsequently from the electric field, then we can find the electric flux density. So in free space now, um, let's say, I mean, this term here is corresponds this term here corresponds to the electric field contributed by an infinite charge density, this term here. So this term here contributed by the infinite charge density. And the flux density is just multiply with the E multiply with the permittivity of free space. So which is equivalent to the charge density. Okay? The charge density. And same goes for, if let's say if it's a volumetric uh, charge density, then we evaluate E in terms of integral. So if the charge density is some kind of a arbitrary volume, as an arbitrary volume, then we have to find then when we evaluate the electric field, then the evaluation of the arbitrary charge object must go through this evaluation, okay, of the to calculate the electric field. So similarly, D can be represented um, in terms of this evaluation. However, perm- without the permittivity of free space. So so therefore, here we can see that the electric flux density, it is independent of the medium. So let's take one example. So let's try one example here, and then we will continue next week. So one example here. Determine D at this point. Determine D at this point. So determine D at this point here. If there's no point charge, -5 pi microcoulomb. Sorry, if there's a point, if there's a point charge -5 pi millicoulomb at this position, and a line charge of this along y-axis, right? So calculate the flux at this point. So what you need to do is we need to um, find what is the electric field at this position contributed by the point charge at this position, and also the electric field, and also the line charge along y-axis. So we consider, when they say along y-axis, that means it is considered as an infinite line charge. So if it's an infinite line charge, then um, so if the line charge is along y-axis, it can be considered an infinite line charge. Um, lying on y-axis. So the electric field, it is rho L divided by 2 pi epsilon naught R, right? R cap. So this R here is the radial direction that is perpendicular, that radial direction that is perpendicular to the line, that is perpendicular to a line, right? Just let me check. I just hope that I didn't write the term wrongly. Sorry, not this one. Yeah, correct. Okay. So if it's along y-axis, therefore at this point, so if it's along y-axis, therefore at this point, so x, y, z, right? So therefore the r, so imagine that you have a line like this. And this is your line charge, right? So this is your line charge. So the perpendicular, so the distance, the radial distance perpendicular to this line, to this green line is your line charge, yeah? So which is lying along y-axis. That means the perpendicular distance uh, to this line charge is always in the x, is always in the xz plane. If you can see this, so it is always in the xz plane. So because it's perpendicular, right? So it is always in the x and z plane. So for what they call it. So sorry. Let me just rewrite this. So it is equals to 3 pi millicoulomb times -3 divided by 2 pi epsilon naught. Okay, 3 pi epsilon naught times the distance r, as I said, is going to be 4 squared plus 3 squared square root in the rho r direction, right? So it is 3 squared plus 4 squared, 3 to the power of 2. Sorry, is, yeah, 3 to the power of 2. So R is magnitude, is the magnitude of from this point here, from this point. So it's 4 trees here, as I said. So 4 3 is around here. Yeah, it's along is on this plane here. So this is 403. Yeah. So here is 4. Here is 3. Yeah. So by right we have we should write this as 4x cap plus 3z cap, right? Sorry, this is not 3 over 2. My mistake. It's square actually. So 3 squared plus 4 squared. Yeah. So because this is a square root of 3 squared plus 4 squared, r cap is also the vector divided by the magnitude of this, the magnitude of this. So therefore is 3 squared plus 4 squared. Okay. So this is equals to then pi and pi. So we have what? So 1.5 times 4 and 1.5 times 3 divided by 25, right? So divided by 25, 0.24 x cap and plus 0.18 epsilon naught z cap. So whole thing is multiplied with to the power 3. So the last part is the point charge. The point charge of this. So which is at here. The point charge is lying at this point here. So the point charge is lying at this point. So the distance here is 3, right? The distance here is 3. So let's say the E field contribute. I just make an index just to differentiate. So E1, index 1 is contributed by the line charge, and E2 is the point charge. So which is -5 pi times 10 to the power -3 divided by 4 pi epsilon along y-axis. So it's so since the point charge is at this position, at this I mean the black dot position that I have just placed here. So it is directly above this. It is that I mean it is directly below this point. So the distance is 3, right? That is 3. I mean the distance from this point to here is 3 square. So it's 3 square y z direction. Sorry, in the z direction. So it is in the Z direction. So adding both. So adding E1 and E2. Oh, sorry, I've overshoot some time. Sorry about that. So we continue. We continue next week. Um, so basically, we just add E1 and E2, then multiply with epsilon naught. So we'll talk again. Uh, all right. Cockwing. Can you stay back if it's okay? Yep. All right. Thank you, everyone. Sorry. Take your time. Yes, Cockwing.